Sehr geehrter Professor Voevodsky, sehr geehrte Angehörige von Paul Bernays, sehr geehrte Damen und Herren. Es ist mir eine besondere, große Freude, Sie zu den 3. Paul Bernays Vorlesungen begrüßen zu dürfen. Die Paul Bernays Vorlesungen sind dem Andenken an den herausragenden Logiker, Mathematiker und Philosophen der Logik und Mathematik Paul Bernays gewidmet. Paul Bernays lehrte und forschte von 1933 bis 1959 als Privatdozent und Professor an der ETH Zürich über Logik und Grundlagen der Mathematik. Paul Bernays gehört zu den Begründern der Beweistheorie und zu den Pionieren der axiomatischen Mengentheorie. Und er lieferte einflussreiche Forschungsideen in der Philosophie der Logik und der Mathematik. Die Paul Bernays Vorlesungen alternieren zwischen der Philosophie der Logik oder Mathematik und der Philosophie der Physik. Die diesjährigen Paul Bernays Vorlesungen gelten der Philosophie der Mathematik und der Logik. Ich freue mich sehr, Wladimir Voevodsky vom Institute for Advanced Study, Princeton, Preisträger der Fields-Medaille von 2002, willkommen zu heißen. Und ich bin gespannt zu hören, was er über die Grundlagen der Mathematik, über Prädikatenlogik und Typentheorie und schließlich über Univalent Foundations sagen wird. Nun möchte ich das Wort an Professor Giovanni Felder, Direktor des Instituts für theoretische Studien, weitergeben. Er wird Wladimir Voevodsky genauer vorstellen. Bitte schön.
Vielen Dank, ich werde auf Englisch fortsetzen. So, ladies and gentlemen, it is a great honor for me to be able to introduce Vladimir Voevodsky to these lectures, and I'm sorry I will take some time of his lecture for this. So, Vladimir Voevodsky was born in Moscow and studied mathematics at Moscow State University, where he was awarded a bachelor degree in 1989. He then went to Harvard University, where he got his PhD in 1992 under the supervision of David Kashdan. So what sounds a brilliant, straightforward career start was certainly brilliant, but not without difficulties. This has to do with the fact that young Vladimir considered attending courses a waste of time, as he was saying in an interview, and that the first impact with America was such that he decided to go back to Moscow as soon as possible. He nevertheless returned to Cambridge to write his thesis in a very short time. He then became a junior fellow of the Harvard Society and stayed at Harvard until 1996. From 1996 to 1999, he was associate professor at Northwestern University. During this time, he was supported by a Sloan Fellowship. In 1999, he was awarded a Clay Prize Fellowship, and since 1999, he is at the Institute for Advanced Study in Princeton, first as a member, and then since January 2002 as a professor in the School of Mathematics. Vladimir Voevodsky made fundamental contributions to mathematics. He was able to use ideas from algebraic topology, and in particular homotopy theory, to obtain deep results in algebraic geometry. One of his spectacular results is the proof of the Milnor conjecture, which is one of the reasons for which he was awarded the Fields Medal at the International Congress of Mathematicians in Beijing in 2002. This conjecture states that the Milnor K theory ring of a field of characteristic different from 2 is isomorphic to the cohomology ring of its Galois group with coefficient in the integers modulo 2. So this results relates K-theory, which finds its origin in topology, with Galois theory, originating in the theory of solutions of polynomial equations of Évariste Galois. So in 2009, he extended his result to prove the Bloch-Kato conjecture, which is a version of this Milnor conjecture where 2 is replaced by an arbitrary prime number. So these striking results are just very special cases of a rich theory invented by Voevodsky, introducing idea coming from topology in algebraic geometry. This theory includes a homotopy theory for algebraic varieties and motivic cohomology, which is a sort of mother of all cohomology theories, and encompasses various previously known theories such as the Ram cohomology, Étale cohomology, and the theory of Chow groups. Voevodsky showed that ideas from topology, once properly understood, are unexpectedly and surprisingly powerful even for solving very algebraic problems. So already in the early 2000s, while he was completing his program towards the proof of the Bloch-Kato conjecture, Voevodsky started to think about what to do next. I understand that he explored several research directions, including faraway topics such as biology. The research he's presently interested in, and is a subject of these lectures, combines foundations of mathematics with computer science. He explained a motivation for exploring this direction in a courageous talk he held at the Institute for Advanced Study, in which he addressed the embarrassing question of mistakes in mathematics. He showed, using example from his research area, including his own work, that sometimes mistakes in complicated mathematical proofs go unnoticed by the authors of these proofs. They go unnoticed by the referees who have to check this before publication, and they go unnoticed by the mathematical community, which is then led sometimes to believe in wrong results. The sophistication of modern mathematics is sometimes so extreme that it is very difficult for the authors themselves, and even more for the referees, let alone the readers, to be sure that all details in a complicated proofs are correct. And indeed, mistakes are usually not discovered by carefully checking proofs, but rather by finding contradictions with other results. One way out of this embarrassing situation is to write proofs in such a way that their correctness can be checked by a computer. This requires writing proofs in a way that computers can read them and verify them. As Voevodsky shows, and he will probably explain this to us, this leads to questions in foundational mathematics. The Zermelo-Frenkel set theory, which is the axiomatic system we are taught since less than 100 years to consider as the established foundations of mathematics, is not suitable for translation in a computer language, as it is too complicated and not algorithmic. A better alternative, which is central in Voevodsky's investigation, is type theory, or more particularly Martin-Löf dependent type theory, a formal system whose elements and rules of deductions can be implemented on a machine. What Voevodsky shows is that while ordinary set theory can be formulated using type theory is actually richer and can be interpreted to describe homotopy theory. This homotopical interpretation, more precisely a homotopical model of type theory, suggests a new axiom called univalence axiom, which Voevodsky proposes to add to the foundations of mathematics. A new theory called homotopy type theory, connecting topology with logic and computer science, was born, and libraries of computer validated proofs are being written. The first systematic exposition of this theory is a 600 pages book called the HOTT book, H-O-T-T book, full title Homotopy Type Theory, which is a remarkable collective collaboration collaborative work, and it was written by the participants of a year dedicated at the Institute for Advanced Studies in 2012-2013 to this subject. The book is truly collective in the sense that everyone, even you and me, is invited to participate and improve the book, which is available online. Let me not steal more time from the lecture and finish by saying a few words about another area in which Voevodsky displays a special talent. Many of us were at the Princeton Institute for Advanced Study and observed the peculiarities and habits of the very special beings dwelling in that honored house. Another activity of Voevodsky is to observe and photograph other less visible but no less interesting animals living around the institute, such as turtles, dragonflies, and herons. Vladimir Voevodsky takes beautiful photographs of these animals, and I recommend that you look at his shots on the website of the institute. I look very much forward to your lectures.
Sorry, this is here. So let me get comfortable with this device here. And so thank you very much for a great introduction. I'm very flattered by it. And actually today and in the two lectures tomorrow, I will be mostly addressing the issues which kind of which are a little bit different from what, for example, the book is dealing with. So I'm really going to speak about the history and philosophy of foundations of mathematics as I see them at the moment. So I actually did a lot of learning for these lectures, and I read a lot of stuff which I didn't know before, and I kind of tried to understand what is the place of univalent foundations, which we're building now, in the long story of foundations and foundational ideas in mathematics. So I did come up with some picture, and I will try to present this picture and to show why I think that it makes sense. But it is in some sense it might also be considered as a kind of research lecture, but rather in history and philosophy of mathematics than mathematics itself. So I'm going to start with this. So I've been to the 8th Asian Science Camp in Singapore a couple of weeks ago, and there were 300 kids from 29 countries of Asia. So there were like 10 people from each country, and there were 29 countries. There were countries like Brunei and Nepal, and there were these guys in these very strange uniforms from some kind of Nepal Buddhist school, and it was really interesting. And I gave some lectures about actually foundations of mathematics and what I was doing and mistakes and stuff like this. And one of the results, later they had a poster session, and that was one of the posters produced by them. So so this is a very colorful young view of foundations of mathematics. But I'm going from this to go into slowly into kind of more into older matters. So one of the things which I did at some point, when I kind of understood that with my own definition of what foundations are, maybe I'll have time to tell what it is, but when I tried to build the lectures around my definition, I understood that that would require so much work that I don't have time. And so I decided maybe I'll do it in one of the lectures in the future. But then I said, okay, so I give up trying to build lectures around my definition, so what about Wikipedia? And I go to Wikipedia, to the page of Foundations of Mathematics, and this is the first paragraph. And actually it turned out to be very, as often happens with Wikipedia, very useful. So let me read it. Foundations of Mathematics is the study of the basic mathematical concepts and how they form hierarchies of more complex structures and concepts, especially the fundamentally important structures that form the language of mathematics, also called meta-mathematical concepts, with an eye to the philosophical aspects and the unity of mathematics. Now, when I tried to make sense of this sentence, which is not so easy, I understood that suddenly a lot of things kind of clicked in my head, and I understood why I was having trouble building the lectures, kind of the structure of the lectures. And it turns out that there are actually two sentences here which are put together, and that was actually hitting me in many of my studies, that there are actually two meanings which people put into the word foundation of mathematics. And when we disentangle them, things start getting some structure and clarity. So there are actually two sentences. One says that there is the study of basic mathematical concepts and how they form hierarchies of more complex structures and concepts. The other sentence says it's the study of fundamentally important structures that form the language of mathematics, also called meta-mathematical concepts. Just a second. So I decided that I'll call the first. So that I decided then I'll go through various things which I've been looking at, and we'll try to disentangle it. That I will call this first thing Foundations 1, and the second thing Foundations 2. So Foundations 1 will be about the structure of the mathematical. The structure of mathematical knowledge in terms of how various concepts derive from each other and connect to each other, and what are the basic ones from which everything can be defined. And the second one will be about the language which we use to do mathematics, about the formal rules of reasoning, about the symbols we use, about kind of the theory of formal systems which we use in doing mathematics. So by that time, there was a particular book which I came to like a lot. And so this book is, this is actually a front piece of a 16th century edition of the original, which of course not the one which I read. So I was reading a translation. So this is a book by a guy whose name is Proclus, and I really came to like him a lot. So he was he lived in the later part of his life in Athens in the 5th century, and he was the successor. He was kind of he had the highest kind of priesthood, in a sense, in the Neoplatonic tradition, which at that time, it's also very interesting because, so 5th century AD, Roman Empire, so Christianity being accepted as official religion in the beginning of the 4th century, so that been like 150 years or 100 years after the acceptance of Christianity by the emperors. So Christianity is starting to kind of really push out everything which is not Christian. And so these guys are, so the Neoplatonists are basically the last remaining remains of the pagan tradition and pagan philosophy and all the stuff which was before Christianity. So one of the Proclus teachers was a guy whose name was Porphyry, and who has this famous book which is called Against Christians. So they were kind of they really didn't like Christians. And they considered Christians to be basically barbarians who came and kind of with their weird ideas and who cannot kind of. But so they really were the remains of that tradition, which now, of course, we have a chance to look at more objectively and without the prejudices of either side. So. So he was the head of Neoplatonic school, and so there is this element, and this commentary, this book, comes with a prologue, very extensive prologue, like about 100 pages, I think, that contains very, very interesting discussion. It's difficult to get into, but once you get into their kind of approach, it becomes really interesting discussion about their thoughts about mathematics in general. And so he summarizes their Neoplatonic view of the view of their tradition on mathematics as follows: mathematics occupies a middle ground between the intelligible and the sense worlds, and exhibits within itself many likenesses of divine things and also many paradigms of physical relations. That actually is then expanded, and one can really make sense of what he has in mind. So I will not go into that side of things too much, but maybe on some other occasion. It's really interesting discussion about the place of imagination and in mathematics in particular, how we visualize mathematical objects and how does it fit in this Platonic hierarchy of things. Is it intelligible, or is it matter, or is it sense object? Is imagination a sense object, or is it an intelligible? And he has some good things to say about it. So he also discusses, and that's also where things get very interesting, because he also discusses the values related to mathematics and sciences in general. And of course, when I was growing up in Moscow, I didn't know anything about Proclus. Actually, I didn't know anything about him until about a year ago. So, but I remember how we all mathematicians from the mathematical faculty of, well, not faculty, the mathematical school of Moscow University, how proud we were that we're doing pure mathematics. And we would go and tell our friends that mathematics is this great thing which is above kind of the applications, which has value of its own, and that that's the beauty and the greatness of it. And then now I open Proclus, and I start reading Proclus, and I find a sentence which just directly reflects the same, exactly the same feeling. We must therefore posit mathematical knowledge and the vision that results from it as being worthy of choice for their own sakes and not because they satisfy human needs. And there are more of these things, which very very interesting. We thought that it's our kind of something which is new and only in our age mathematics became such a great thing that we can say these words. So then closer to foundations of mathematics and mathematics. So one of the first things which he says, and now I'm trying to partition things into foundations 1 and foundations 2. And so there are things which are not related to foundations, like the previous things, and then the things in foundations. Can we categorize them in foundations 1 and foundations 2? So the first thing is the Pythagoreans considered all mathematical science to be divided into 4 parts. One part they marked as concerned with quantity, the other half with magnitude. And each of these they posited as twofold. A quantity can be considered in regard to its character by itself, or in its relation to other quantity. Magnitudes is either stationary or in motion. Now this way of structuring mathematical knowledge, we'll see it in future slides, was amazingly persistent and repeated in various forms by great mathematicians later. And so the first thing, so the magnitude is continuous, is what we would say continuous quantity. So kind of in Euclid, the size of a square is a magnitude, and also the length of a line is a magnitude. So so these are magnitudes. But by quantity, they meant strictly a discrete thing. So quantity is a number, and a number is just a thing which is obtained by taking several units and placing them together. So, so quantity here means basically a discrete quantity in our words, and magnitude means a continuous quantity. Now, when they further subdivide, so quantity considered in regard to its character by itself, I'm not entirely sure how we can separate in contemporary view a part of mathematics which deals with that, but there will be a comment a little further, and then in relation to other quantities, and then he illustrates it. Yes, and I'm saying here I looked into the history of types in general, types in our contemporary sense, the ways of separating mathematical entities in different kind of classes, and apparently the first such example was the appearance of types for variables in Fortran in 1957. And there were exactly two, the integers, the discrete and floating point continuous. So there was exactly this separation. And now, the secondary division in this classification, Proclus illustrates them as follows, that arithmetic then studies quantities as such. In music, the relations between quantities. So, of course, in music, the relations between integers are important for various formation of various musical things, but that's a little too far from our view. And then geometry studies magnitudes at rest, which makes sense. That's what it is about. And then spherics, magnitudes inherently moving. And spherics refers to astronomy. So in their view of things, the study of movement, of kind of ideal mathematical movement, was the study of movement of planets, for example, on their spheres, like in their old Greek models, their things were put on spheres, and presumably that's why it was called spherics. So that now it does make sense to spend some time on it and to get familiar with it, because this approach to foundations of mathematics, that's kind of foundations which they have. That's the foundations one which existed at their time. So that was separation into basic categories. Then Proclus says that there is a different approach also. And he says that, but others like Geminus think that mathematics should be divided differently. They think of one part as concerned with intelligibles only, and of another as working with perceptibles and in contact with them. Of the mathematics that deals with intelligibles, they posit arithmetic and geometry as the two primary and the most authentic parts, while the mathematics that attends to sensibles contains 6 sciences: mechanics, astronomy, optics, geometry, canonics, and calculation. So that's a different approach to subdividing mathematics, which is something which we have in the structure of our education and our universities. So there is mathematics pure and mathematics applied, And then mathematics pure, of course, is subdivided into arithmetic and geometry, which we also hear a lot about. So that, all of this goes back to 5th century to Proclus, at least. Probably goes back deeper. But here it's definitely expressed in a very clear way. Now, one thing which Proclus does not talk about is the division of mathematics into into constructive and non-constructive. And this is something which is really important for in the Univalent foundations, development of Univalent foundations today. But of course, this is not reflected there. But something surprisingly is reflected. There is quite a bit of a discussion about whether it's right to call all. So it's a commentary on Euclid. So at some point he goes from this introduction to actually commenting on individual definitions and propositions in Euclid. And before that, he kind of discusses the construction of Euclid elements. He says that some things are called their problems and some things are called their theorems. And is it really right? And this is the main discussion about foundations too, which I could find. So this is about, well, I think it should be placed in foundations too. One can argue, but I think it's meta-mathematical issue. At least today, it's certainly meta-mathematical issue. So let's see. I will explain what it is about. I'll explain what is a theorem and what is a problem in a few minutes, and why it's important to care about the difference. So proposition is used in a very general sense here. So some of the Asians, however, insisted on calling all propositions theorems, considering theorems to be a more appropriate designation than problems for the objects of the theoretical sciences, especially since these sciences deal with eternal things. There is no coming to be among eternals, and hence a problem has no place here, proposing as it does to bring into being or to make something not previously existing, such as to construct an equilateral triangle. Others, on the contrary, thought it correct to say that all inquiries are problems. So this is kind of totally relevant to Univalent foundations. I mean, we just, let me go here, just a few months ago we had, and I think this argument is still ongoing, and I'm still kind of trying to insist on my position here. And a lot of people who are in particular involved with the homotopy type theory book are trying to insist on a more on a different position. And this is really a curious place where this kind of fight between primacy of logic versus kind of primacy of mathematics is happening. So here is a quote from Martin Löw, from a very important paper he's called Constructive Mathematics and Computer Programming from 1979. So he says about some form of expression which is used in his theory, that this kind of expression can be read in three different ways. It can be read that A is an object of a type, or it can be read that A is a proof of the proposition, because in modern constructive type theory, propositions are considered to be types, kind of sets, whose elements are their proofs. That's how we deal with it. So for us, proving a theorem is the same as constructing an equilateral triangle in a sense, because it means constructing a proof, and proof being an object which has to be constructed. So, but then the question arises, because it's kind of really it's really cool to consider propositions to be types, but then there is a certain movement which says that okay, we can consider propositions to be types, but now all types are propositions. And so then every construction in the world is actually a proof of a proposition, and then everything is again kind of subsumed by logic in a kind of in a totally bizarre way. So so there is this, but also he writes A is a program for the problem task A. So these three kinds of types, in a sense, the general types, types which are propositions, and types whose objects can be interpreted as programs. This we have now, and we discuss it, and this is a current issue, and as you can see, it was a current issue with a lot of argument in Proclus' time, except in a slightly kind of less. I would say at his time it was less precise, and they had much fewer examples than we have, so we can build things much more. In a much more detailed way. So now as we move forward from Proclus, I'll jump from Proclus to another favorite of mine, and the next favorite of mine is actually Grassmann. But on the way we'll stop a little bit. There is a great quote from Gauss: "The subject of mathematics is all extensive magnitudes, those in which parts can be conceived. Intensive magnitudes, all non-extensive magnitudes, insofar as they depend on the extensives. To the former class of magnitudes belongs space, time, number. To the later, velocity, density, rigidity, pitch of tone, intensity of tone and of light, probability, etc." So here we don't have the four groups. We only have kind of two groups, which then so he kind of, we can say that he, but still the approach to classification is still philosophical one. There is this one big thing which is kind of murky, and to understand what is inside, we start splitting it in smaller parts and giving them names. And so that was Gauss. And by the way, this is an extremely interesting and difficult to, I mean, it's not, there is meaning to it, which is, which I'm trying to kind of understand it better, because the question of analysis and constructive analysis is one of the most difficult ones in the current development, in particular for univalent foundations. And we really have, there is really something is missing in our understanding of continuum, of how to formalize continuum. Of course, there's this formalization in terms of Cauchy sequences or Dedekind cuts, and these things do give some approximations, but it's more or less clear now that there is something more should be here. And what Gauss talks about here is quite interesting, and you can probably kind of feel it, that there is a difference between space and like location in space and velocity. Indeed, if you have space, you can talk about a piece of space. But if you talk about velocity, you cannot talk about a piece of velocity. I mean, it kind of doesn't make much sense, right? So in that sense, so it does appear that when one really formalizes things in this more in this less simplistic way than it's done now, then there will be differences between, so the things like velocity belong to different real numbers than position. So the two real numbers which appear in this in these two contexts are kind of different real numbers. But that's something which I'm thinking about, and this gives me some ideas about kind of the examples and so on. And I wouldn't be so surprised that actually probability lived in some third kind of real numbers. And then when we have this, and then of course, anyway, so let's see. So now there is Hermann Grassmann. Unfortunately, I didn't include his, should have included at least one picture of his. he is a very interesting character, and he wrote this book in 1844. Actually, I was going to ask somebody to read it, to tell me how to pronounce it in German, and I forgot. So I don't know how to read it in German. Okay, thank you.
Extension theory, if you translate that literally. Ausdehnen, to extend, Lehre,
To learn, teach. Okay. So he was in this book, of which I only read the long preface which he wrote, which is not as long as Proclus, but also quite long, and where he also discusses his view of the philosophy of mathematics. And now, so we had Proclus, which was 5th century. Now we have something from 1844. And before he actually starts discussing more general things than just mathematics, and I find this quote to be very, for me, it was very useful in understanding the view which they had at that time. So nowadays we're taught at school that mathematics is based on this theory, let's say Zermelo-Fraenkel theory, and then it kind of grows from this one root and becomes all this beautiful mathematics. So we're taught to see mathematics as having one root in a sense, and then growing from this root. At his time, at the time of Grassmann, it was totally different. They didn't have such a perception at all, and there was a lot of good mathematics, by the way. So he compares mathematics and philosophy, and he says, in philosophy, the overview of the whole predominates, and its development consists precisely in the gradual ramification and articulation of the whole. In mathematics, the interconnection of particulars is emphasized, and separate independent developments combined together, each becoming only a factor in following concatenation. So he didn't see mathematics as coming from one root. He saw mathematics as coming from many different sources, and then kind of intertwining to form a common whole, a kind of a whole. But, so that's how he saw it, but in the same introduction he then says that there should be nevertheless something common to mathematics. And this is actually a key, an important slide, because I will argue that what we are building now is, in Univalent foundations, is kind of extension of this tradition, which I first saw in Grassmann. And I'll explain why I think so. So here's what he writes, and he says that there should be this general theory of forms, and unfortunately I don't have it, so it makes difficult my work. That's what Grassmann says, which it's not on the slide. He says my work is made difficult by the fact that there is no this general theory of forms which I could rely on, so I have to say some words about it. And so he says, by the general theory of forms we mean that series of truths that relate to all branches of mathematics in the same way, and which thus assume only the general concepts of equality and difference, conjunction and separation. That's what he sees at that time, and he further contributes to this Pythagorean tradition and says that he further partitioned mathematics into the theory of continuous form or magnitude in the narrow sense, and discrete or conjunctive form, and then into that arising from the equal, which we may call the algebraic form, and that from the different, which we may call the combinatorial form. So this second, so it's four things. It starts like in Pythagorean version from continuous and discrete, but then the second ramification is different. The second ramification is into that arising from the equal, and that arising from the different. It's quite difficult to understand and make sense of, but what comes to mind, and he also considers what he is doing in his work to be a contribution to the theory of continuous combinatorial. so somehow he thinks of this because the part of the equal is more or less clear. So that arising from the equal, it means, I guess, the structures in which all elements are the same. Like, for example, in number, in integer is a collection of units, and all units there are the same. Real number is, I'm not sure what it is a collection of, but for example, a real line consists of points which are all the same. So I think that's what he has in mind. And but then combinatorial form, of course, there is a notion of combinatorics. I can take these units and color them in different colors, right? And then try to, for example, count how many different colorings there is. So that would be discrete different, and it would indeed be the subject of what we today call combinatorics. But what exactly he means by continuous different, I don't understand. So, but that's what he wrote.
Excuse me, just a very short question. Form. What was he talking about in modern terms?
Yes, thank you for the question. So the word form here is quite can be read in various ways. So I will argue that one of the ways to read it is to read it as shape. And shape is the kind of general. Well, there is no. It doesn't exist in modern terms. I mean, I would actually argue that our types in univalent foundations is one of the ways to make this notion of a form precise. And in fact, also we'll see that Cantor in his writings, he was also talking about building something like a theory of forms. So there is also another reading here. And this reading is the reading of forms in the Plato sense. So Plato had the objects of this intelligible world, which is above mathematics, as you can remember. So there is the world of intelligibles, then there is mathematics, and then there is a world of sensibles. And so these things in this world of intelligibles are traditionally translated into English by the word forms. So there are these Platonic forms. They're kind of, my understanding is that the best way of saying it would be, it's a general concept of a pattern. When you see kind of the two trains, one in China and one in US, look like kind of the same, so similar that you can say that in both cases it's a train. That is because there is this general pattern which allows you to compare two things.
Is it gauge theory? Is it principal fiber bundle? Is it
Well, you see, this might be some other approaches which developed in, but it's not something which we have an answer to, okay. By no means. It's so this word form is very. So let me try to get to. So this is all about Foundations 1, as you can see. It's how to build the hierarchy of mathematical concepts, how to structure mathematics. And basically, this common idea of a common foundation in this general theory of form, where I could first find it was in Grassmann. So now, what about Foundations 2? We only saw this discussion about problem versus theorem. I didn't look into it kind of, I didn't yet have time, I'm going to. But Foundations 2 existed in the Western world in the form of the science of logic with a capital L. So the science of logic was considered to be way above the science or art of mathematics in the hierarchy of sciences. So it was really kind of mathematics was this guides which can count. Logic was almost as high as theology in the scheme of things. So it was kind of way beyond and way above. And because of this, I don't even. No, I don't have it. But because of this, the flow of ideas from mathematics to logic was inhibited, very strongly inhibited. So until the 19th century, and we'll talk about it in the next lecture, mathematics developed a lot in the 17th, 18th century. There were great advances. And of course also advances in Foundations 1. But Foundations 2, it was a question of logic, and it was totally frozen. And the new ideas in mathematics kind of didn't get to it until 19th century when things started to change. So, and that was because of this. And then, of course, Gödel came and completely reversed put logic into the place under mathematics, in a sense. I would say so. But yeah, so this is Proclus about Foundations 2. There is kind of interesting discussion about again in Euclid. We now use just the word axiom. In Euclid, there are hypotheses, postulates, and axioms. And there is an extended discussion about what is the difference between these three. And it goes back to Aristotle. And that's quite curious. And I'm not sure whether it makes, whether it can be found in modern discussions or not. But so I will talk about more about what happened in 19th century and how these ideas of general theory of form evolved on the one hand side, and how the mathematics started to enter into the domain of logic and to affect Foundations too. But I also want today, just for the last 5 minutes, or actually we have more minutes. So sorry, I forgot that it's yeah, we have more minutes. Okay, so I will then let me slow down a little bit and let's see where the general picture of things is. So we have Foundations 1, Foundations 2. We looked at them in a few classical sources. And now let's try to do something which I attempted to do in more detail, but found to be very, very difficult. So I'll just enter there a little bit. And actually, Proclus is great, and reading him is fun, and there are so many ideas which are easy to understand and to relate to. But I also wanted to go deeper in time, and really the first foundational system of mathematics, the first foundational systems of mathematics are the number systems in various Asian cultures. So whether in Asian cultures or in our own culture, but in our own culture, we learn arithmetic so in such an early age that it gets buried in very kind of deep inside our psyche, and it's kind of it's difficult to think about it as being on the same to think about it in the same terms as we think about higher mathematics. But if one does, then one can think about, first of all, let's try to find Foundations 1 and Foundations 2. Or just use them as a clarifying or structuring device. And one can think that actually one starts with just counting, right? The numbers are just numbers. I mean, there is that many, that many, that many. The fact that one can represent them through tens and hundreds, or like in our decimal system, or in other systems maybe through 60s or something like that. This is actually building a hierarchy in this infinite world of individual natural numbers. So this is a conceptual structuring of the world of natural numbers, which we don't really think about as conceptual structuring, but which nevertheless is. And we know from the, I know a little bit just from on the Wikipedia level of the story of Hindu fascination with large numbers, and apparently they had individual names for all the powers of 10 up to something like 52. So each power of 10 had some hierarchical significance and had its own name. Now, these concepts of lesser equal and this stuff is mathematical, and you can see it from the fact that they were written in words. And here we come to the main difficulty, I think, because the real content of arithmetic, of the stuff which we learn in the, I don't know which grade, but the real content is first of all, that the numbers can be written in this way, but also that there are these certain manipulations with the symbols which we can use to get answers about these numbers. So there's algorithms for doing elementary arithmetic. And this is foundations too, I think. Because algorithms, well, at least that's what Wikipedia thinks. Because Wikipedia, if you look at this page again, you'll see that the algorithms are designated as part of the second part of foundations. So algorithms are foundations too. And so we have this powerful foundations too in arithmetic. And if we wanted, ideally, if I wanted to have a definition, a foundations of mathematics is this, this, and that. And then these foundations of mathematics is this instance of this general concept. This foundations of mathematics is that instance of general concept, right? That's how we like to think mathematically. And then I would have to include into my general concept somehow the algorithms. And this is one of the, this again, so Proclus is silent. He only mentions calculation in one part in this Geminus classification. Calculation is considered to be one of the branches of applied mathematics. So, along with optics and canonics and stuff like this. But that's not how we see things today. And for example, in the Univalent foundations, one of the most interesting and complex problems is the integration of the part of foundations which relate to abstract reasoning with the part which relate to computation. So and of course when one does things with a computer, it becomes even more important. And we're discovering interesting things. We're discovering that methods of computations can interact with each other like axioms do. Like in axioms, it's easy to invent one axiom which will be consistent, and then another axiom which will be also consistent, but the two together will not be consistent. So it turns out that something like that happens with methods of computations, if they're understood in general enough terms, that there are certain combinations of methods of computations which are together consistent, and some other combinations also, but you cannot just take things and place them on top of one another. And so that's one insight into how computation should be included in this general concept of foundational system or formal deduction system, which we don't yet have, of course, but we're trying to come up with. And I'm thinking that maybe actually thinking about algorithms as we do them in simple arithmetic can be helpful for the design of our advanced systems, because in the design of our advanced systems, the Platonic side is extremely strong, and there is this very well, Platonic and general classic, there is also this desire to somehow deduce things from some higher principles, and to kind of ground the system of reasoning not in particulars, but in some one grand principle, which is then followed in a kind of dogmatic way. And if we think about the design of our number systems, then maybe that should give us a pause. And the greatest mathematics which we have is really coming from the need to adapt to to what actually is, as opposed to the need to follow some general ideas. Also, general ideas are, of course, what makes it fun. So it's it has to be some sort of a compromise here. Well, thank you. I think that was my plan. I planned for a 1-hour lecture, and I would be happy to have some discussion and questions. Thank you.
Well, I really love that. I'm a little bit perplexed because I'm a mathematician, or at least I used to be one, but I have no exposure to mathematics of metamathematics. And so probably what I'm going to ask will be very, very easy for you. Something like eating popcorns or butterbrot at breakfast. And so if I understand you correctly, what you are alluding at is that mathematics as the logical structure of object-oriented programming, and that in some sense you could try to represent, to map the all mathematics, whatever mathematics was, is, or could be, in terms of, how do you call them, Entwurfungsmuster, development patterns. You know, the 35 or 36 development patterns of object-oriented programming that you can find in terms of UML diagrams, on the basis of which you can basically
which diagrams?
UML, Unified Model Language.
Well, I'm certainly not. I'm not aware of UML.
Okay.
So
it's just a way of talking. We just do you know object-oriented programming? I presume so.
Not really. I mean, I can a little bit guess what you mean from the name itself.
No, because what I heard was data, methods, computations, structures, inheritance, downcasting. These, I mean, you can find all of these concepts in object-oriented programming, one-to-one. And so I was really convinced that you were alluding at that.
No. I was entirely not alluding to that.
Okay.
Let me. You know what? How about we go to some other questions and then maybe return to your question, because I
have another batch of questions completely separated of these.
Do you want to answer or?
No, I think I would like to kind of skip it for now and then maybe return to it later, because I'm really not aware of that paradigm, and I was not alluding to it. So in that.
You started out by telling us about Geminus and placing mathematics between the sphere of the intelligible and the sphere of the perceptible. And then you ended by saying that one of the challenges in the Univalent Foundations program is, so to speak, implementing forms of abstract reasoning within computation. And now my question is, at first I thought this is basically the distinction between pure and applied mathematics, but then I wonder whether that's right. And whether one could say there is the intelligible world, and then there is its implementation in computation, and then the application of the things you've proven, through computation, is yet a different thing. So that both what you here call the forms of abstract reasoning and computation would still be part of pure mathematics, even though, of course, implementing, constructing things takes you to reality. But it's not yet the step to applied mathematics. Have I got that right, or does do you see it differently, and computation is already for you part of applied mathematics?
If I understand one of your questions correctly, it's a question about relation of what we do to applied mathematics. Mm-hmm. I would say that so far we haven't advanced enough to be really relevant for applied mathematics in the Univalent Foundations program. Our friends and colleagues and collaborators who work on general verification systems are very much relevant for applied mathematics. Also, it is a difficult and very it's just sociologically difficult issue, because what we're saying basically is that all these programs for applied mathematics, which everybody uses, nobody knows what they're actually doing, and nobody knows whether they're, I mean, are there mistakes there? I know that in mathematics there are mistakes. Are there mistakes in other programs? What about these programs which biologists are using for computing some stuff with, I don't know, genetic trees and stuff like this? What the heck these programs are actually doing? And they're actually, excuse me for my language, but there are actually two questions. One question is what algorithms they're actually implementing and what these algorithms are supposed to be doing. And another question is whether they're implementing these algorithms faithfully, whether there are mistakes in implementation. So we, of course, are saying that going forward in time, we want to plan for the next 500 years, and we want to slowly move into the world where all such important programs which are used in science will be formally specified and formally verified, and outside of Univalent foundations, but just using the standard formal methods. This, of course, is difficult, and at the moment we have this number which is kind of a little depressing at the moment. So there is a number which I call Hale's number, because Tom Hales was the person who first cited the value of it, current value. It's one takes a computation done in C, for example, just some kind of applied mathematical program written in C. And then one takes the same program and writes it in a form where everything is formally verified, so that all computations are not approximate. I mean, they're approximate where they should be approximate, but all the approximations are taken into account. And it's formally verified, and you can formally prove that the program does exactly what it's prescribed to do, no more and no less, and no more, no less and no more. And so the question is how much slower this verified version is versus the non-verified version. And at the moment, for the kind of proof assistant which Tom Hales used, the coefficients was 2000. And this is really bad. So for us, this is how far we are from being very useful for applied mathematics. We need to get this coefficient down to, I don't know, 10. And so that's...
I have a question that relates to the concept of algorithm. Perhaps you can say a little bit more about what you think an algorithm is, because it seems to me that, or according to the standard story in the history of mathematics, or what I take to be the standard story, algorithms are tightly connected with the existence of machines that can do syntactical transformations and don't. You find it in Grassmann and Whitehead that you have just syntactical transformations without caring about the content of your formulae, and if you are able to do such transformations, then you are using an algorithm. And the standard story is that before Leibniz's machine and Boolean algebra and Grassmann's algebra, you don't have algorithms in mathematics. But you talk about, on this slide, for example, of the algorithms used by the ancients. So you seem to have an idea of an implicit algorithm, that they were using an algorithm without knowing that they were using an algorithm. Is that right? Or
well, they certainly didn't have the word, but I mean, yes, of course. When you add two like 10-digit numbers, you're using an algorithm to do it.
So you think it doesn't make any difference if you believe you are dealing with abstract entities. I mean your liking of Proclus seems to blur the distinction between an understanding of mathematics that is related to abstract entities always, and an algorithmic idea of mathematics where you don't care about the objects you are dealing with.
Well, this algorithmic side is a helper for us to build things in this world of passive nodes. Or I mean, we cannot build anything in intelligibles because it's eternal and fixed. So the world where we build things in mathematics and stuff, it's this intermediate world. And but to build things there and to create there, we're using this algorithmic things as helpers. When you write down something in order not to forget, it's using something physical as a helper to work with things in this intermediate level of nodes, and that's how I also see this all these various formalization programs as creating more powerful helping strategies to be able to build more beautiful and interesting things in there.
Well, I liked your quotation of Martin Löw's the 3 aspects of typing. And one of the aspects is problems, right? And so I have to ask you a question. What is the problem of foundation? And if the problem of foundation is looked at this point of view, from point of view of types, you might be very interested to see how the problem of foundation can be looked at constructively, that is finding a whole system, a whole program of solving the problem of foundation. That's the third, the Kolmogorov aspect. And the second aspect is understanding the problem of foundation in the sense of constructing structure. Now, how do you consider the problem of foundation? As a problem of solving what? And how do you find what the success of the solving the problem of foundation should be?
I will say more about it in the lecture tomorrow and maybe the day after. I mean, in both lectures tomorrow. But first of all, I see I take Gödel's results very seriously, and not only seriously, but I also take them as something good as opposed to something bad. It's not something to fight. It's something to which actually opens for us a road into a very wide realm of creativity, which we wouldn't have otherwise. And one of the things which Gödel says is that there can be no final foundation. So, and again, I will talk about it, and I think it's very important. So the thing which I see is we need a practical foundation which we can use now as a helper in our kind of discovery and development. And we need a process, we need to establish a process which will ensure that this foundation grows in a healthy way. And I have some very concrete ideas about it related to the verification and certification of relative consistency and so on. So that I see these foundations as something which is smaller than the whole of mathematics, but which is growing together with mathematics and remaining healthy through automated verification and certification.
Thank you. I have a comment and a question that maybe you'll answer tomorrow, I don't know. So what the message I took from the analysis of all these different classifications of mathematics by different people is that it reflects more the personal taste of the person who did it, or like the culture at the time, or maybe the state of mathematics at the time than mathematics itself. Like this division between intensive and extensive mathematics, or discrete and continuous, or intelligible and sensible. Maybe it has something to do about how hard it is, or there's no obvious way to go from one field of mathematics to the other at the moment. So for now we keep them in separate boxes, but also about like the taste of the person at the moment. And now we live in this information age, and we're immersed in these algorithms, and this is a new way to look at the world. And we are now reformulating mathematics in these terms. And in what sense will this be more fundamental than saying discrete versus continuous, or intensive versus extensive? Is there any hint that this is something more, something deeper?
I'm not entirely sure what more fundamental means. I think it is a good sign when in the new when in new framework we can look back at the old framework and understand it. So since now we can still understand this distinction between continuous and discrete, and we're actually still interested in it, and there is some possible there are things there which we still don't understand, but we understand the general idea of continuous versus discrete. So for us, this is clear. What we are building allows us to understand what was built before. In that sense, it's more advanced than what was before. Is it an answer?
This would have been precisely my other set of questions. So, because if I remember correctly what you alluded or mentioned, you were mentioning about difficulties in measuring velocity or speed, problems from in space, going from discrete to continuum, the other way around. And so were you alluding at quantum gravitation?
No, I was not alluding
precisely what Liz Molin and company are doing.
I was not alluding to quantum gravitation, but I am alluding to general difficulties in contemporary physics to some extent, because one of the things which comes to mind, clearly they do have kind of hardcore stuff in their theories, right? Because they can compute things and things then and predict real things in to some extent. So, but I have this idea, which not necessarily doesn't have to play out, but
please
there is this idea that one of the reasons why we have difficulties with physics is because our mathematical understanding of continuum is not sufficiently detailed and is not sufficiently exact and complex to reflect what we really have in the material reality.
Which brings me to my last question. You were alluding at something, difficulties in probability, numbers, probability, the sum.
Well, I also said that, yes, that the probabilities are real. What I was saying is that, well, actually, I was alluding to something very concrete. In constructive mathematics, when one takes definitions of real numbers, which are all equivalent in classical mathematics, and then repeats them in the constructive mathematics, then one gets definitions which are not equivalent. In the case of real numbers, it doesn't seem to be very important because for various technical reasons. But there are other examples, like definition of a field, for example, like algebraic field. In classical mathematics, there is one notion of a field. In constructive mathematics, there are at least 4 different concepts which all converge into the same concept of a field when one assumes classicality. And so in constructive mathematics, it's typical that existing classical concepts kind of ramify into several concepts. Now, one would hope, maybe not at this junction kind of development, maybe in the next 50 years or something, but one would hope that at some point maybe this vision of Gauss can have some meaning when the concept of real numbers will split into several concepts and will have different notions of continuum. And the coordinate will be an element of one kind of continuum, and velocity will be an element of another kind of continuum. And this kind of continuums will converge when we assume some strong axioms, but in more subtle kind of more detailed understanding, they will be different. And because of this difference, we'll be able to deal with some problems in physics. And then I also said that probability probably would belong to a third kind of continuum, which is neither coordinate nor velocity.
Yes.
So that's what I was alluding to. I was alluding.
You are preparing the basis for solving some unsolved problem of constructive quantum field theory.
By what?
Constructive quantum field theory.
You know, there is this person. If you want to hear more about it from a really kind of
We have to ask.
hardcore perspective, there is Urs Schreiber.
Yes.
Urs Schreiber.
Yes.
Is one of the active persons on NLab blog space and NCAD. Okay. And he has been building this interesting ideas about how Univalent foundations can be extended further into kind of adding to them some new components, extend them into foundations of synthetic differential geometry, and through these foundations of physics in terms of type theory. And he has some concrete ideas about it. I refer you to him.
Can you introduce me to him?
Well, he is very active on various blog spaces. I don't think he needs to be introduced. Well, we can talk about it by email.
Okay, I suggest we stop here, and you'll have plenty of opportunity to ask more questions tomorrow afternoon. Let's thank Vladimir Voevodsky again for this.
Thank you.